My name is Bruce Richardson, and I'll be talking about robotics today. Basically, my history is I have a lot of experience in developing robotic systems for not only for automation in R&D, but also in commercial products and in production facilities. So we'll be talking about that today. So the agenda is kind of why automate, first of all. Why would you want to automate, and the pluses and minuses of automating. We'll talk about, like I said, robotics and research. So research and development. So if you're working on the development of a new product, how we can speed up your process by using robotics in that area. We'll talk about commercial products automation, what kind of automation is used in commercial products and the benefits of different applications. Manufacturing automation. A lot of people are developing products that require automation in manufacturing, so that we'll talk about that also. And then we'll kind of generalize later on about when to automate. And when to use robots in production, and then talk about conclusions and some recommendations. So essentially, why you want to automate is key things is probably time savings. And not only time savings saves you money, but it can also save you time and development process by speeding up the overall process. So you obviously can increase throughput. Robots can run all night. I have CNC machines in my facilities, which is a special time automation. And we run those all night long, and it's a great way to increase your productivity. And then some areas, especially in research and development, it enables you to do other tasks rather than just doing simple mundane things. Obviously, time is money, cost savings, like I said. And then also the space. They're actually a very efficient use of space. They don't need a kitchen, they don't need a bathroom, and then also they can be very compact. A lot of areas, fatigue reduction is a very important aspect of automation. We actually have one case example where that was actually one of the driving factors. Another area is consistency and quality. If you want something that's very delicate, like injection into GC mass spectrometers used to be very delicate and user specific. So if you want good consistency, sometimes robotics is very important. Also timing, microplate dispensing, the timing of that process can be very critical, so actually automation can solve that problem. Dispensing of epoxies is another area. And then obviously special environments. You may either be working in a biohazard lab or in a lab that has maybe special chemicals, so a robot can also solve some of those problems. So specifically talking about R&D, some of the types of robots that are used are typically Cartesian or Scaro robots. This is a picture up here of just actually one of our robots, an XYZ robot. A Scaro robot works more like your arm, essentially kind of a rotational, linear type application. There's also some high-end microplate automation that is really beneficial for high throughput screening or different types of chemistry applications. And this actually shows a Douglas system, which can run like about 100 microplates a day. So essentially, R&D, you're typically using off-the-shelf type applications or off-the-shelf automation. You're not customizing. You may have to customize a small amount because of the specialty of the application, but usually you're looking for a really quick return on investment, getting the automation in, getting it running right away to help with your research and development. And you really don't necessarily want to spend a lot of time with custom equipment. So that's kind of what we'll focus a little bit on today. So the first case study we have up here is a system was used for a detector injection. So basically this company was injecting a sample into a detector. And there were problems with that particular system in the sense that the injection samples were very time consuming, and they actually came at a frequency that wasn't easy for the user to do it. Every 1 to 2 minutes you had to inject, and that timing was somewhat critical. And so you'd stand around for 1 or 2 minutes and then inject, and then stand around for 1 and 2 minutes inject. So you wasted a lot of time, and because it was tedious to do, automation was a great possible solution. The only thing is the company really had a limited amount of capital. They didn't want to go out and spend $60,000, and it really didn't pay back. So what we ended up doing is coming up with a low-cost Cartesian robot. And actually how we were able to accomplish that is we basically bought a used Biotech system, which is a standard microplate robot up here in the right-hand corner. And essentially we modified that, did some simple modifications to allow the upfront automation. And you know, the system was purchased for $3,000 on eBay. If you were to go out to buy a new one, it'd probably be $40,000 to $60,000. But it worked out really nice because we were able to get the system in real quick, get it up and running, and get the simple process automated. So the outcome is basically the assays are being performed by the machine rather than the scientist. So the scientist is able to do a lot of analysis and other higher level work, while the machine robot, or the automation, is done by the robot. The actual results are more accurate or consistent. The timing is pretty much precise. And then the interface to the injection system is also controlled, so they're getting a lot better results. And then one really important thing with this particular case is they were working on a new technology, and what they've learned actually in the robotic system here is being applied to the commercial product that will be released later on. So if you looked at the cost analysis, I like using Accel for doing almost anything, but this is a perfect example of using it for a cost analysis. So what we did is we looked at the initial investment for the automation, we looked at the resource, the full-time employee annual cost, and what percentage that he was actually doing to run this assay or being used to run this assay, and calculated out what kind of savings you would get. So if you plot over time, this being months, the black line essentially is the initial investment of $12,000, but the amount of expenditure over every test or every month was reduced because less labor was used for that test. Essentially, this line here is just without automation, so every month you keep paying more and more for this person to continue to do the experimentation. So the crossover point ends up being about 4 months, so it was a pretty quick payback. Now, if you ended up spending $60,000 up front, the payback would be way out here. It may not pay off, but using this creative solution of actually buying something off at the internet and getting it up and going was a real good way for somebody to get up to speed. So some of the creative approaches that you can use in R&D, one thing is I'm a real big fan of Craigslist and eBay. Like I said, we bought that robot there. One thing is when you buy a complex robot, there's usually sometimes a month or 2 month delay. With eBay, you can get it in a week or so. Now, there is a risk that it may not work, but you also have the risk if you buy a really expensive robot and try and automate your R&D process, it still may not work. So the small investment that you have, I think it's worth taking the risk. And or there's a lot of vendors that are very established on eBay that will guarantee it. So it actually is a pretty safe risk. The other thing is used equipment dealers. You know, I live in the San Jose area or work in the San Jose area, so there's a lot of used equipment dealers there. Then they will actually let you demo the unit, test it to see if it works in your application before you buy it. So it's actually a very good approach if you're in that area. And then think outside the box. I think this is a great show because it does have a lot of other people here, other kinds of technologies like the aerospace upstairs, but semiconductor capital equipment can be a good way of finding out what other types of automation equipment that may be specialized per your type of R&D problem. Then automation in products. Essentially, you know, when you develop a commercial product, there's always a certain amount of automation in there, or not always, but probably it's used more in diagnostics products than it is in medical products. But they're typically custom designs because they're so specialized and there's cost constraints that you have to live under. Cartesian robots are a very common you know, application. Probe arms are used in there, carousels, reagent cuvette readers, but almost anything you can think of that's used in commercial products and automation. So one thing, because it is so specific to the application, we focused a little bit more on actually how do you identify what is the best opportunity. And the one thing is obviously you want to look at the workflow of the process. You know, what kind of procedure or what kind of protocol is being run, understand the environment, and then also do some kind of an idea, get an idea of how many tests per hour or how much the machine is used per hour, what amount of labor rate is being used, how much automation do you really need. And once you develop in developing the requirements, you should probably come up with a workflow analysis or a flow chart that actually shows you, you know, the process that you're going through, and then look at those individual process steps. The other thing is to question whether you really need automation through the entire process. I've worked on projects where the upfront sample processing is fairly complex, or you can do that with another automation solution. So maybe consider just starting at the middle of the process, or maybe the tail end of the process is something that's easy to automate offline or with a separate piece of equipment. Classic thing is an incubator and a reader. You may not integrate those two in the first set of automation or first product release. So really the flow chart gives you the ability to determine where you want to automate, and then using some kind of a spreadsheet or analysis, we'll kind of show you an example later on. You can kind of go through and determine what's the most important automation to hit or to develop first. So Cartesian robots are used quite a bit in automation of custom products or in diagnostic products, so we kind of took that as a little bit of a case example. Like I said, custom designs are used quite a bit. That's an example of a diagnostic instrument off the right. The positives with that are that you get exactly or at least close to what you want as far as performance, costs, and so forth. The negatives are it does take time and money to develop that robotic system, and your team may be better off used in core technology or proprietary technologies working on those areas rather than redeveloping the wheel. OEM components, you can buy linear stages and put those together, but those have a tendency to be costly, even though it does save you time, money up front. In the long run, the product's going to be probably a little bit more expensive than it needs to be, but that may be the correct solution anyway. The other option is to use an OEM robotic subsystem and integrate that OEM system into your system. And the positives there is you can be up and running pretty quickly. Limited resources or capital are required up front. And then our robot is one example where we can actually scale it and make it fit your application at a reasonable cost. There are other vendors out there. The negatives that can be come into play are the limited flexibility. Essentially, some of the OEM vendors only sell certain sizes, so you have to be careful of that. And then also, you might run into a single source situation where you only are able to get that from one supplier. That could be a problem too. And also, other OEM robots can cost maybe a little bit more, and so you really have to evaluate whether or not you have the right solution for your product. Creative approaches for automation and products. Again, I love eBay and Craigslist and so forth. The one thing there is to actually use that to look at other products that potentially have it's been done before. Like I worked a lot on immunoassay diagnostic systems, and now I'm working a lot more on DNA type systems, but a lot of those old immunoanalyzer systems had a lot of neat technology in them, and you can buy them for a fraction of the cost of, and bring them in-house and take them apart and understand what they're doing and learn from those devices. Like, for example, the Abaxis Piccolo up there was a really trendy product 20 years ago. You can buy it online for a few $1,000s, and there's a lot of neat technology that you can learn from. Patents is also another area that's really a good way to get up to speed. If you're new in the area and you want to look at what other people have done in similar market areas, you can get online with Google real quick and find out what other people have patented. It may not be the same technology they're working on, but at least you can use ideas from other people's test devices or commercial products and learn from those. The other thing on a commercial analyzer, where you have a process or a protocol, and this can kind of be adapted to almost any phase of the development program or even production, is using Microsoft Project as a timing diagram. You can spend a lot of money and get a custom timing program, but if you use Microsoft Office and use minutes for seconds, you can actually analyze a fairly complex analyzer and the timing diagram for that. It gives you the ability to size and scale the device in a creative way without a lot of investment, a lot of time, and basically you can use, like for this example, the robot is in blue and it's a resource like a human being. You just put it in there as the robot as the resource. So you can do resource leveling, you can do critical path analysis, which you can optimize the throughput, and then you can scale it and change it around and see what the final analysis is. So it's a really great way. I actually did this for a project when I was working with Roche, and they use this really fancy timing diagram or timing program, and they ended up adopting this in their system. So the other types of automation are automation used in production, which is probably a big application for customized robots. Most of the stuff is customized. Some off-the-shelf components are used, but they're usually more components. Usually large and expensive. Again, they use pretty much all kinds of creative techniques to get the job done. And you can pretty much almost anything you think of can be used for production automation. So case study number 2 was a disposable device that we were working on, and they came to us and asked us, hey, how do we cut the cost of this device, and how do we improve our margins? So the initial production cost, or at least the labor portion, was about $44. They were only at this time doing about 3,000 units per year, and the goal was reduce costs with automation. Well, we considered a couple solutions. One was basically a low-end automation where we just automated key steps in the process, and then the other one was a high-end automation where we automated a lot of the steps. And essentially what we did is we did this, again, similar type ROI analysis, return on investment analysis, where we looked at the investment. So the low end was just doing a couple stations at about $40,000. The high end was a couple $100,000. And if you really looked at it, the amount of savings of time, and there was really one person that was actually running the operations. And really, when you added the automation, you'd still need that one person. So if you really ran the numbers, it turned out it was 24 months before the low-end automation would ever pay back, and it took years probably for the high-end automation. So we kind of said to these guys, I don't really know right now really if you should be doing any automation. And they were really gung-ho about trying to save money, but based on the volume that they had, they weren't going to save any money. So with this simple analysis, it was pretty clear that they shouldn't invest a lot of money in automation. What they should do is invest money in other areas. So the outcome, again, was it would take 2 years to do payback. Really considering the best area for them to save money was in actually their cost of materials, is reducing the material cost by going to molded components or combining or outsourcing, so they didn't have to spend any more money on automation but spend money in other areas. And also recommendation for this is wait until the sales increase or before adding automation, so it always doesn't pay. So some creative approaches, again, I come back to the eBay thing, like bowl feeders, all these special pieces of equipment. It may not be a bad idea even if you're not going to use it in the final production version, but to be able to buy some components, play with it, test it to make sure it works okay, then order the exact piece of equipment. We've done that with ultrasonic welding equipment. Buy a used one first, get the application running, use that older system as a backup, and then buy a new system from Branson that fits your application and use that as your primary one. Also, one trick thing is using the CNC machine. We have a fair number of CNCs in our facilities. They're actually very cheap. That mini mill is about $45,000. And I've seen people adapt those. We actually use ours for an optical inspection system, and we put different mounts on it. So if you have a really special, hyper-precise automation process, sometimes it may be better to actually just to modify one of those, and that can actually be used to help you get through those early stages. And/or I've heard of people modifying hundreds of these things for a specialty automation process. The other thing that we like to do, I'm not sure if you're familiar with the microplate format, but for diagnostics, it's a very common platform. And there's a lot of automation equipment like this is a stacker. Here's a rotary arm system, and the microplates are in here. And basically, for a fairly low amount of money, you can get very high-end automation solutions without a custom application. So we've been able to recommend to customers that they use a microplate format. So if you're filling like maybe little syringes or reagent packs or even any kind of a thing for a medical device, where you can fit that into this like about 3x4 square area and put little receivers there, you can take the advantage or the benefit of all these pre-designed pieces of equipment to move these little trays around with the small components in there. And then really what you have to do is make the individual process steps that are specific to that application. And for microplates, they do a lot of automated filling stations, so you actually can buy that as a off-the-shelf component rather than customize it yourself. So it really gives you the ability to get a lot of automation and do it quickly without a huge investment and do it in a step-by-step fashion. Obviously, if the product is close to the size of a microplate, we were doing a DNA reader for biodefense, and their cassette was about the same size but not the same size. And they came to us and said, hey, we want to do automation of the loading of the cassette. And I said, well, if you just change the size of your cassette, you could buy an automated loader for about $10,000 and your design is done. I kind of cut myself out of a lot of business because we could have designed something custom for them, but it was a real enlightening thing for them, and they changed the design, and actually that's what they used for their front-end loading. Obviously, as your product's bigger than that, you're kind of out of luck, but it's a really cool product area that you can use for either production and or obviously for diagnostics too. So when do you want to automate? And so basically what we like to do is come up with multiple scenarios. We've just shown 3 here, but you may want to do multiple scenarios if you're looking at it. And this can be used in not only in research and development for finding out whether you're going to save labor time and get more testing or more experimentation done in the development process. It can be used, as you can kind of see earlier on, for products that have automation in them, or it can be used for production automation. So basically, you're usually trying to come up with a baseline, which might be manual. It might be manual assembly steps. Another scenario would be partially automated, and maybe the third scenario or multiple scenarios would be fully automation. So you got to have a flow process in place. You understand or at least estimate the time per step, and if you're doing it manually, obviously you take that as a baseline. You can calculate what you're doing right now. Estimate the cost to implement each step of automation. So if it's a sealer station or whatever, you can either potentially find some equipment or just guesstimate about what it was going to cost, and then create a cost model. So essentially this is the basic cost model, and essentially over here are the different process steps. There's a setup time, which even in automation you have. There's different process steps, testing, packaging typically. So this is an example of just how much full-time employee time is spent on the individual steps. And what we did is just took an hourly rate, multiplied it by the time or whatever, and came up with a cost per step. For this thing, it's $18 to assemble this component. And I think this was based on 100,000 units, so every year you're spending $1.8 million in assembly labor. Some people are taking pictures. If you want to, at the end of the show, we can give you this presentation. Then scenario 2, what we did is say, hey, and usually this is what you do. You want to look at maybe the steps that are costing you the most amount of time. This is 10 and 5 minutes. And maybe step 1 is easy to automate, maybe it isn't. But let's say you put $40,000 in each one of those process steps to save time. And you're not going to completely save time, but it maybe takes a lot less of the operator's time. You put an estimate there. Well, with an investment of $80,000, you're talking the price almost went in half because you're saving those key time steps in the process. The third scenario, basically we automated almost everything except for obviously the setup time. And there's a significant amount of capital for each of the steps, so maybe $250,000 of processing. And again, these numbers are all relative. If you use the same process for either a smaller or larger analysis, it still comes out the same. So this is a graph again, and over a 12-month period, this red line is essentially the manual thing where you didn't spend any money. This is where the minimal amount of capital was spent, and the payback time is in about 4 months. So it definitely pays to go ahead and do these stations early on. And compared to that last example where it took years to pay off, this was a good payback model. And then the automation takes about 6 months. So this probably would be worth it to go to the $250,000 of tooling. It depends on if you want to spend that capital early or later, and maybe a staged approach is also better. So the next slide starts getting into the conclusions, and essentially one thing I always like to do is consider staging the automation, whether it's in the development process or actually in the production process, is look at your key steps. Like for example, this is an example of a rotary processing station using microplates. So you had a loader here, a Scaro robot in the middle that would move the disposable through multiple process steps. And to do this all at once might be a little bit aggressive. So working on some of the key process steps one at a time and getting those optimized, and again tying that back to the return on investment analysis, those may be the more expensive steps or the more trickier steps that are to do. So essentially focus on those first and then move into this maybe later on once you get the individual steps or processes running. So in general, basically, I like to use a spreadsheet to analyze the process and the payback. You can do that in a day or two and really get an idea of how much automation is going to make you successful and what the best automation approach is. And it always doesn't pay back to do automation, as you can see in the last are the first case studies. So a lot of people assume it, and it may not be the case, and or you have to be smart in how you stage it. I think the other thing is be creative, and you can find a way, you know, by using some of the ideas of eBay, used equipment, patents, and so forth. You know, just think outside the box. And then I think obviously the show is a great show. Go around and talk to people and find out what they have to offer. And most of the time they're ready to help you for free. So it's a good way of learning about automation. So that's basically it. We're at booth 607 if you want to say hello to us, and or I have time, or do we have time for some questions? A couple minutes if you have any questions. Great. I guess no question. Like I said, if anybody's interested, you know, we can send you the presentation. We'll actually, I guess, get some of your information, and we'll send out a, you know, a thing that says if you want to, you can email us, and or you can just email Accel Biotech and ask it. And I have spreadsheets too that you can use as a baseline if you'd like. Thanks a lot.